The first theorem is more or less is kind of a summary of the things that we did before. So here it says if we have a limit of a function here we have limit of fx, right? That means it's not specifically a sequence but a general function, right? And if the limit of that function is equal to L, say for example if we consider the function as x over x plus 1, which is the same thing that we did before, and here the limit of this function when x goes to infinity was equal to 1. And this theorem says if we replace everything by n and name it as an, in other words, if we replace everything by n, that means it becomes a sequence where n is an integer, so it becomes a sequence, then the limit of that sequence is also equal to 1. So this is basically the same thing written in a more nicer way, and it is expressed as a theorem, right? So if we consider the function, and if x goes to infinity, and if the function converges to a certain value, then that means if we replace the domain values with integers, and if we write down the equation, then it becomes a sequence, and that sequence will also converge to the same value. Let's do another example that goes with the above theorem. What if we need to find the convergence of this sequence? Now, when I write a certain term, you should properly identify whether it is a sequence or a general function. Now, if I mention the terms with n, that means it is a sequence. In other words, here we are considering this sequence. ln, that is logarithm, so I will write it like this, then it will be more clear to you. And here we have the sequence starting from 1 and goes up to infinity, and we are supposed to find the convergence, or in other words, we need to find whether this sequence converges or not, right? So at once, if we just plug in infinity, then the logarithm of n when n is a large number will be infinity, and the denominator will also be equal to infinity. That means this becomes an indeterminate case. So what should we do? Normally, when you have these logarithm stuffs as a fraction, L'Hopital's rule will come in handy. But the thing is, L'Hopital's rule should only be applied for a function defined throughout the real numbers. But here it is not like that. This is kind of a discrete function. Okay, so we cannot differentiate these kinds of stuffs, right? Because to differentiate you need some sort of a continuity, right? But if we are only considering some discrete points and the values related to those discrete points, we cannot differentiate such a function, right? So we need this sort of a continuity for us to differentiate in the first place. Okay, so what we can do is, instead of considering this sequence, we can have a look at the corresponding function. Now see, here we had a function at the beginning and we converted it down to a sequence. Now here we should go in the other way. We have a sequence and we need to look at the corresponding function, right? So if we look at the corresponding function, then it becomes ln x divided by x, right? And then we can see whether you have a limit for this function, this continuous function, and for that we can use the L'Hopital's rule. L'Hopital's rule says the same limit you can obtain by differentiating the numerator and the denominator separately, right? So this becomes the limit of x goes to infinity. This is 1 over x is the derivative of ln x, and 1 is the derivative of x, so this becomes 0, right? In other words, the limit of this function, when x goes to infinity is equal to 0. And how did we obtain this function? We consider the corresponding one with this sequence. Okay, so let's move to that theorem we mentioned at the beginning. It says if we have a function and if it converges, then the corresponding sequence will converge. And here we started with the sequence, which is this one, and then so our sequence was an was equal to the logarithm of n divided by n, right? And the corresponding function was equal to ln x divided by x, and we had a limit for this function when x goes to infinity. And from the theorem it says then that limit should be equal to the limit of this sequence. So that's what the theorem says. If we have a limit for this function, it will definitely have a limit for this sequence. So it's like this sequence is like a subset of the function, right? So, and when I say a limit, we should consider the limit of the function when x goes to infinity, right? Okay, so from this theorem we can say that our sequence converges and the value is equal to 0. In fact, we can write the limit of an when n goes to infinity is equal to 0, right? So this directly comes from the above theorem, okay? Because keep in mind, we cannot use the L'Hopital's rule for this sequence at once, right? We should convert it to a function and then use the L'Hopital's rule, and we have a result from the L'Hopital's rule. That means we have a limiting value, or the limit of this function converges, and from the theorem you can say that the sequence will also converge to the same value.